Okay, Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our class ET4 to 6 Power Electronics 2. So in this lecture we will learn about the thermal management. So basically in thermal management we will learn about the thermal characteristic of the device and how the device can heat up, okay, the component such as the diode and MOSFET. So we will focus on that two components. And then at the end of this topic you should be able to design or choose the thermal heatsink that we can use to ensure that our component is kept cool down during the operation. So basically in this lecture we will learn about the thermal basic, in which we will study the relationship between the dissipated power and the junction temperature. The junction temperature is the temperature at the device itself within the component. And then we will see the phenomena of thermal runaway. And then after that we will go to the thermal management, how we can design the heatsink for MOSFET and the Schottky diode. Okay, when we are talking about the converter, okay, I think you know that we have four type of converter, whether from AC to DC, AC to AC, DC to AC, or DC to DC converter. The objective of all the converter is to deliver power from one form to other form, okay, but maybe different, okay, for DC to DC maybe at different voltage level, okay. And then when we have the converter, you know that they will involve a switching mechanism, okay, there will be a switch on and off. So this conversion process will generate heat, okay. So you have the input power, and then you have a switching action inside of the converter, and then you have the output power. Inside the converter there will be some heat produced by the switching action, and also due to the losses lah. Okay, so that's why we are going to learn about the thermal basic, the characteristic of uh, the thermal characteristic of the component, of the electronics component, so that we can understand more and then we can do something about the heat. Before we go detail into the thermal basic, we have to learn the comparison between the electrical circuit and the thermal circuit. Okay, we have the electrical circuit, and at the same time within the same circuit you have the thermal circuit, okay, but this is the analogy. Okay, for the voltage in the electrical circuit is equivalent to the temperature in the thermal circuit, okay. And then for the potential difference or voltage difference, is the same or comparable to the temperature difference. And then you have the current in electrical, current in ampere, and then for the thermal it is equivalent to the power dissipated. The power in electrical circuit is equal to the heat, okay, produced in the thermal circuit. And then we have the conductivity, okay, and then you also have the thermal conductivity for the thermal. For electrical circuit you have resistivity, and the thermal circuit you have the thermal resistivity. Okay, this is the dissipated power versus the junction temperature or the temperature graph. So we have the ambient temperature. This is the temperature of the surrounding environment, or we can call it room temperature. And then we have the junction temperature. This is the temperature of the silicon die within the package of the device when it is powered. So what is the junction temperature? Is the temperature inside the component itself. If you have the package of the MOSFET, so this is the inside of the MOSFET, the temperature inside. Okay, so we have the ideal world condition. This is what we want. which is when we have the increase in the dissipated power, okay, power dissipated within the device due to the switching action. When we have the increase in the power dissipated, the temperature of the device or the component remain the same. Okay, this is the ideal what we want. Okay, but in actual, when we have the dissipated power, the junction temperature also increase. Okay, so when the power dissipation dissipated is increased, it will contribute to the increase in the junction temperature. Okay, the higher the power dissipated, the higher the junction temperature. Okay, in this graph it shows the power dissipated versus the junction temperature, but you can see there are two different line with different slope. Okay, so the higher the slope, it means that the lower the thermal resistance and the higher the rate of change of the power dissipation. Okay, and then for the lower slope, lower angle of slope here, so it means that it have the higher thermal resistance. Okay, and then it contribute to the lower thermal conductivity and lower dissipated power. Okay, when we are dealing with the device power dissipation and the temperature graph, there will be two lines that we are interested. The first one is the device power dissipation versus the temperature itself, and then the other one is the straight line from the ambient temperature that we have and touching the line of the power dissipation and versus temperature of the device. Okay, so if the if the slope of the line are the same, so what it means is this is the nominal operating point, which is the system heat removal is equivalent to the device dissipation. Okay, so in this case the dp removal over dt is equal to the rate of the power dissipated versus the time. Okay, so I will show the example about this in the later slide. Okay, in this case we have two line as well. The first one is the device PD over T, and then the next one is the system heat removal graph, or dp removal over dt. So if the dp removal over dt slope is higher in terms of slope compared to the device pd over dt, this one, so it means that the rate of change of we try to eliminate the heat is greater than the rate of the heat produced itself. So in this case the junction will cool down. Okay, so the dp removal, usually this one represented by the characteristic of the heat sink that we have. So let's say the device is producing low heat, but the capacity of the heat sink is very good, so it easily can remove the heat from the device. So this one will be very good. Okay, and this one is for another extreme. We have two line as well. First one is the device power dissipated versus temperature line, and then if we have the system heat removal or dp removal over dt, which is less, okay, in terms of slope, which is lower than the slope of the device pd over t, and then it means that the junction will heat up. So the heat produced by the converter is too much, okay, and the heatsink itself don't have enough time or enough capacity to dissipate all the heat from the component itself. So this will be a problem, and it will cause problem to your device. Okay class, this is the typical device power dissipation versus temperature curve. So normally you will get this curve. You can get this curve if you buy any component such as a MOSFET or the diode. You can have this curve in the datasheet of the device. Okay, and then here a comparison, okay, of the three slope that you draw from the ambient temperature. And then you have several regions that I want to show you. This is the first region. So in this region, okay, when you draw the line from the ambient temperature to any point at this region, so at this point the dp removal over dt will be higher than the dpd over dt. Okay, the dpd over dt is, okay, remember this is the power dissipation, power dissipated versus the temperature curve. And remember, this is the delta power dissipation versus delta T. What it mean by delta of this is the slope of this. Okay, if you still remember when you learn math, the slope of this graph at this point should be a straight line at this point that touching this point. Okay, the slope at this point will be a straight line and touch one point at this point. Okay, the same, if you want to find the slope at this point, it will be straight line here. Okay, so that's what it mean by the dpd over dt. Okay, and then the slope here, okay, is the dp removal over dt. So if you have the point at this region, it means that the dp removal over dt will be higher than the dpd over dt. Okay, we take one example. Let's say at this point, at this operating temperature, the dpd over dt will be, okay, maybe I can draw a line. This is the straight line you draw here. So this is the, we call it the slope of the line at this point. Okay, and then the dp removal over dt at this point is this one. So you compare this slope and the right one here, so it means that the dp removal over dt is higher at this point. Okay, and then we have at this one, the line here, the dp removal over dt is equal to dpd over dt. Okay, so this line at this point, the slope of the dpd over dt is, okay, the lines, the straight line here, and then the dp removal over dt is also the same line here. So at this point, we know that the dp removal over dt equals to the dpd over dt. Okay, now we move to the third region of this curve. So this is the region after the boundary condition here. Okay, we have the boundary condition here, and then any point that exceed this boundary condition, you can find it the dpd over dt, mean the curve or the slope at this point is higher than the dp removal over dt. Okay, let's say we take the blue dot as example. So at this blue dot, you can see that the slope of this, okay, imagine you have a straight line connecting to the blue dot. So the slope here will be much higher compared to the straight line from the ambient temperature to the blue dot. Okay, so that's why you have this area. Okay, now we want to see some example. Okay, this is the first operating point. Let's say this is the junction temperature of one component. Okay, and then at this point, if you have the straight line, okay, connecting the ambient to this point, okay, so it means that the dp removal is much higher compared to the dpd over dt. Okay, so in this point, you can see that this operation or this operating point is stable. Okay, and then we have a second case where the operating point or the dpd over dt of the device, this is the at this point the power dissipation of the device, and this is the temperature of the device. So we can see that at this point the dp removal, okay, the slope is lower than the dpd over dt, so this is the unstable region. And then we have another case, okay, where the dp removal over dt is equal to the dpd over dt at this point, so this will be a boundary condition. So the area after this boundary condition can result in the thermal runaway. So this is the effect that will cause a problem to the component itself. Okay, in the next section we will look at the non-linear characteristic of the power dissipation versus the device junction temperature of the component. So the one that we are interested to learn is on the MOSFET and also the diode. Okay, and then you know that the curve has a boundary operation junction temperature above which the power dissipation will be higher than the removal capability, and this will result in thermal instability. Okay, in the next section we will learn about this thing. Okay, so you have to know that the Schottky, off-state and MOSFET on-state exhibit a non-linear power dissipation curve versus the device junction temperature. So we are specifically focusing on the Schottky off-state and MOSFET on-state. So these two characteristic or operating point that exhibit the non-linear power dissipation versus the device junction temperature. Okay, and this one will make, okay, if we operate above the boundary operation, so it can result in thermal instability.